Hello, lovely viewers. I'm excited to inform you about my new course on Udemy titled Practical Multi-Amp Bandit Algorithms in Python, as you can see on the Udemy Marketplace. Now, this course was born out of the many positive feedbacks that I received from you guys, either on my phone via WhatsApp or through my email address. And some people even requested for one-on-one tuitions. And so I thought a more scalable solution is to publish a course on Udemy, and I'm happy that I've been able to pull this out. Now, this hands-on course focuses on the multi-amp bandit problems, which involve building agents that are capable of consistently choosing the best action out of a limited set of options by learning through trial and error. And I also understand that not everybody enjoys seeing mathematical formulas. And so I intentionally stay away from complicated mathematics. And I only bring in the maths when it's necessary. And instead, I teach how to painlessly translate seemingly complex mathematical formulas into Python code. So if you know basic algebra and basic programming in Python, then this course is the best online course for you to kickstart your career in reinforcement learning, starting with multi-amp bandit algorithms. And the approach I took is a very hands-on one. And so in a single Jupyter notebook hosted on Google Colabs, I guide you through every step as you learn how to build intelligent agents that are capable of balancing between exploration and exploitation using various algorithmic strategies such as epsilon-greedy, epsilon-greedy with decay, soft mass exploration, optimistic initialization, upper confidence bounds, and several other algorithms in there. And so just to give you a summary of what's in the notebook, I basically start off by showing you how to create an environment to simulate the dynamics of a multi-amp bandit problem. And once we have created this environment, we sample each arm a couple of times to validate that indeed the reward probabilities that we observe are similar to what we have encoded in the environment. The next thing I show you is to um, be able to calculate the average of a large set of numbers without necessarily having to store all those numbers in a list, because the traditional approach is to store the entire set of numbers in the list, and then you sum them and divide it by the length of the list. But for reinforcement learning agents that are built to run very long in production, you agree with me that the size of your list is going to grow linearly with time, and so it becomes computationally expensive, especially in terms of memory. And so this incremental sampling technique helps you to be able to calculate averages without the need to store entire list of numbers. So basically, you're calculating average on the fly. And I show you two techniques, one that uses a fixed step size and one where it is dependent on how many times each arm has been sampled. And so I show you a graph to let you understand what the impact of the fixed step size is, especially on multi-arm bandit problems where the reward distribution is dynamic, so it's not stationary, and so it changes over time. And so this um, incremental sampling technique helps you to be able to capture the dynamism in such environments. Then from there, I build a random agent with you to help you to have a baseline with which you are basically going to compare the performance of other algorithms that we implement. So the random agent basically just acts randomly in the environment, and so we don't expect it to have any good reward in terms of what it receives from the environment. And so we also make plots side by side for each algorithm that we implement. We make a plot of how the um, reward increases over time, and we also make a plot to see what the agent is basically doing in terms of how it chooses each arm or each option available to it in the NAB problem. And so after the random agent, I also implement the greedy agent with you. So the greedy agent is at the far end of the random agent. The random agent behaves randomly, while the greedy agent behaves greedily. So they are at the ends of the ladder, and so we are able to compare and contrast the two to see how they differ from each other, and we convince ourselves that none of them is the best really, because the random agent kind of like pulls the arms randomly, and the greedy agent settles not always on the best arm because it is greedy, and the moment it sees a payout from a particular arm, it sticks to it, and so it doesn't even explore the other arms at all. Then we start off by learning a better way of balancing between exploration and exploitation, where exploitation means using the knowledge the agent has about the environment to affect its behavior, and exploration simply means taking random actions to be able to learn more about the environment. Okay, and so we need to keep a balance between exploring and exploiting because they are both important, and if you stick to just one of them, you don't see the best reward from your agent. And so with a strategy called epsilon-greedy, we implement the epsilon-greedy agent, and we see that indeed the agent is able to figure out the best arm to pull, and it also samples quite a number of times from the different arms based on the reward distribution. And we go on to a more intelligent way of exploring using what is known as softmax or Boltzmann distribution. And this is where my strategy of not focusing on the complex mathematics becomes very important. So over here, I explain intuitively what this formula means, and then we go ahead to translate it into Python code, because I also believe that as programmers, it is easier for us to think in code more than in formulas sometimes. And so we're able to translate that formula into code, and we also confirm that indeed that agent is able to learn the best arm or the best option out of the available options that the agent is supposed to learn to select. And I also introduce you to another way of inducing exploration using what is known as optimistic initialization under the umbrella term optimism in the face of uncertainty. And so we talk about how you can initialize the Q values to certain values that is going to let the agent start off by exploring, and we are able to convince ourselves with the plot also that the agent is able to learn the best arm, and indeed it also samples the other arms quite a number of times. And we also go ahead to learn about realistic optimism with upper confidence bounds. So upper confidence bounds is similar to softmax exploration, and the difference is that with softmax exploration, the agent just starts off being optimistic. He behaves as though it is in heaven and everything is right. But the UCB agent is basically an agent that wants to be realistic about its optimism and how it explores. And so it includes a measure of uncertainty for each of the Q values that have been learned, and that goes to affect how it behaves in the environment. And once again, we're able to see that the agent learns the best arm to pull, and it also samples a number of it samples the other arms a number of times. And so I encourage you to enroll now using the link in the video description below for the best deal, and I hope you enjoy every lesson as much as I enjoyed making them. So thank you, and see you in class soon.